Today we're going to find out how we find the distance between a point and a plane. Now we're going to keep it really kind of interesting. We're not going to put the point on the plane because how would that be boring? Distance is 0. Instead we're going to keep a point off a plane. So we have a plane right here and we have some point Q off that plane. In order to do this, before we get to the formula of it, let's take a look at more about what's kind of happening here in terms of the geometry of it. Now, if I draw a straight line between the point and the plane, I am going to get this perpendicular line right there. Now, from the other video, we remember this as being the norm of a plane. In other words, it is a vector perpendicular to the plane. Now, if I knew where this point was down here, it would be really easy to get that distance. But math isn't that easy for us. So we really can't find that point. So what we do instead is we're going to arbitrarily find a point anywhere on this plane instead. And I'll call this point A. Now, I can find any point on a plane. It's like finding a point on a line. We'll talk about that in just a moment. But let's say I knew where this point was. We will, but right now let's say we'll keep it an arbitrary point. Well, I can write a vector from A to Q. Right there. I can write this vector, and I can even find this vector. It would be vector AQ. And I can even find that vector right there pretty easily to do. Now, but I want to find this norm right here, the length of this norm. So the question is, well, how can we find the length of this norm if I know AQ? Well, we have to remember a little bit something. This is one norm from our vector. But remember, from our plane. This plane has infinitely many norms to it that are all perpendicular. Now, all of these little norms have one thing in common. They are all perpendicular to the plane and they are all heading in the same direction. I can use this fact to help me get this length right here. Even though I don't know where on the plane this particular norm is located, I can use the fact that all these norms have in the same direction to help me get the length of this magnitude. And the idea I like to show people is this. Imagine you have an airplane flying in the sky. There's my airplane flying in the sky. Now it's traveling in a straight line. Well, whether the plane is here, and let's say it never changes altitude to here, ready? This distance over here is a norm because it's perpendicular to the ground. Well, as the airplane moves, I get another norm. Now, what do you notice about these two norms? They're exactly the same. As long as that airplane never changes altitude, the length, the distance from the ground to the plane never changes. So it really doesn't matter where we put that norm. The height, the altitude never changes. Heck, I could even be crazy and put my norm over here where the plane hasn't reached yet. The distance between this point and the ground will still be the same as the other two. The same idea is here. This point Q will always be the same distance from this plane no matter where we move it. The distance is not going to change. So if I draw this norm up here, it's going to be this. If I continue with this norm here, it'll be the exact same length as this norm up to point Q. So we don't really need to know where n is. We just need to find a norm, and that's any norm. And we're in luck because remember, if we have a plane, the equation of our plane, right, is going to be like ax plus b y plus c z equals some d right here, right? We can get the equation of our norm by looking at the coefficients of our vector, a, b, of our plane, So the norm vector is going to be the same as the coefficients of our plane. So let's take a look at an example. Let's say we have a point A, and it's at 1, 3, negative 1. We'll call that point A. And we want to find the distance to the following plane, x minus 2y plus z equals 0. And I want to find that distance right there. Well, the first thing we're going to need to know is a point on the plane. So I call that step 1. We need a point on the plane itself. Now I told you we can find any point on a plane. So if this is my plane x minus 2y plus z equals 0, I can find any 2 points by solving for x and y, picking values for x and y. I'll let x be 0. Yeah, I know y can be 0, but let's not be boring. Let's let y be 1. And I find z. Well, if I solve for z, I'm going to get 0 minus 2 plus z equals 0, and we get z equals 2. So we have a point on our plane, 0, 1, 2. Next, we need the norm of the vector. Well, to get the norm of the vector, we don't need the norm. We're going to have to find the vector AQ. So we're going to find the distance between this point on the plane, which we'll call that point Q here, I guess. Doesn't really matter, I guess we call it. I know it doesn't match up here. I kind of switched them around. But I want to find this vector from the plane to the point. So I'll call this vector, Q, A. And if I do that, we're going to subtract, of course, 0 minus 1, so I get negative 1, 1 minus 3, negative 2, 2 minus a negative 1, and I get 3. And there's my vector. So right now, this is what I have. If I were to kind of look at this, ready? If we were to kind of look at this, we have point A not on the plane, and I put point Q on the plane. So I now have this vector right here. Okay? Next, I need a norm. Any norm. I know I really want this norm. I want any norm, okay, on that vector. So I'm going to go ahead and find that norm real quickly. And again, the norm comes from the coefficients of our plane. So the norm would be 1, negative 2, 1. Now comes for the fun part. How do we find the length right here? Well, from earlier we learned about projections. This norm right here, and the norm goes all the way up. I only want this little length right here. That is a projection. So what we want to do is we want to find the projection of, in our case, QA onto the norm itself. So if I can find that projection, that's going to give me the equation right here. That's going to give me this length right here. Well, in a way, that's actually going to be a projection. Remember, this is going to be a vector. So if I want to make this a length, we change the formula a little bit. So let's take a look. So we have an equation for us. Sorry about that. So we're going to have a little bit of an equation for us to find the distance. It's going to be our projection formula. Okay? And it's going to be the magnitude of the projection. Magnitude, because it's a distance, has to be positive. We'll talk about that in just a minute. Of our point QA on N. And this is going to equal, again, the magnitude of the dot product of QA dotted with N. Just like our projection, right? Divided by, now, the magnitude of the projection. Now, earlier when we first did projections, it would be divided by the magnitude of n squared. You might remember this. It was divided by the magnitude of n squared. It would have been times, and then we would multiply it by n. But because I'm looking for the distance, I'm not looking for a vector. See, that gave me a vector right there. This is just going to give us a scalar. In this case, the distance. So by getting rid of one of the n's right there, we get the distance that from the plane to the point. And so let's go ahead and do that. So we take the dot product of Q, A, and N. And that's going to give me the magnitude of negative 1, plus 4 plus 3 divided by the magnitude of n, which is going to be the square root of 1 plus 4 plus 1, and on top here what we're going to wind up with is, what do we get here? 6 divided by the square root of 6, or root 6. And this would be the distance. Okay? I hope you enjoy this video. If not, don't tell me. But enjoy. I'll talk to you later. Bye-bye.